Good morning, guys. In today's class, we're going to see about computational modules in embedded system. So, in this computational models in embedded system are of 6 types. So, one is data flow graph, second one is control data flow graph, third one is state machine model, fourth is sequential program model, fifth one is concurrent or communicating process model, sixth is object-oriented model. In that, first we're going to see about data flow model. So in this data flow graph or data flow model translates the data processing requirements into a data flow graph. So the data flow graph model is a data-driven model in which the program execution is determined by data. So indeed, data flow graph is visual model in which the operations on the data process is represented using a block that is of this circle. So in this circle, we're going to represent only the operands, and the data flow is represented using arrows. So these are the arrows. So where the arrow mark is, it was in inward arrow. So an inward arrow to the process represents input data, and an outward arrow from the process represents the output data in data flow graph. So here in this example, we are taken as x is equals to a plus b and y equals to x minus c. So this following figure illustrates the data flow graph. See, x equals to a plus b. So what we need to do, we need to get a plus b, which is equals to x. So now this is a, we're going to keep it as a, and this is b. So by using inward arrow, the arrow mark, we're going to combine it with an, in this circle we're going to represent only the operands. So we are representing the operands place. So by combining this, we're going to get an a plus b. So in this we're going to get a plus b, and here is the output x. So here x is equals to a plus b we got from this. From these things we got x is equals to a plus b, and next y is equals to x minus c we need to get. So x, the operand is minus, and the c we are taking from here we of in inward arrow, and we're going to get my y. So y is equals to x minus c. This is what the data flow graph is about. I think you guys have understood. So next is control data flow. The second one is control data flow graph. So here in this controlled data flow graph, the DFG, the data flow graph model, the execution is controlled by data and it doesn't involve any control operations. So in earlier cases, what I'm speaking about is earlier cases, there was no any conditional operations or the control operations. But here in this control data flow graph, we have some conditions. By using these conditions, we're going to execute. So the control data flow graph is used for modeling applications involving conditional program execution. So the CDFG, that is control data flow graph modules, contains both data operations and the control operation. For an example, if we take if flag equals to 1, x is equals to a plus b, else condition, y is equals to a minus b. So this is an example what we have taken. We're going to represent this example using a control data flow. So this is the condition which has been added in this control data flow graph, whereas here there is no conditions in data flow graph. So this is the condition. So the condition they have given it as if flag equals to 1. So if, so this will be represented using in a diamond block. The conditions will be represented using in diamond block. So where flag equals to 1. So we need to get to whether it is true or it is of false. Whether if the condition equals to 1, if it satisfies, then it becomes true. If it is of true, what it will going to get? A plus b. So we're going to get an a plus b. So this a plus b will be of x, which will be moved to the out, which will come out. So if my flag is of false, this is else condition. If my condition is false, then what it will going to do? It will going to perform a minus b operation, a minus b operations, and it will going to come out. So at last we're going to come, we're going to get what the desired output, what we need to get. I hope you guys understood. The condition is flag. If flag equals to 1, it should execute x is equals to a plus b. If it is a false, it should execute y is equals to a minus b. So here flag is true, hence it will going to execute a plus b. If it is a false, it will going to execute a minus b. This is what the control data flow is of. So next is state machine model. The state machine model is used for modeling reactive or event driven embedded system whose processing behavior is dependent on state transition. So the state machine model describes the system behavior with states, events, actions, and transitions. So here the state is a representation of current situation. An event is an input to the state. So the event acts as stimuli for state transition. So transition is the movement from one state to another state. So action is an activity to be performed by the state transition machine. So these are the 4 things which we're going to perform in this state machine model. So as an example, we're going to see, let us consider the design. So let us consider the design of an embedded system for driver passenger seat belt warning in an automotive using the FSM, that is finite state machine model. So state machine model, F indicates the finite state machine model. The system requirements are as this. So as we guys know, as an example, let we take as in car, when the car ignition is turned on and the seat belt is not fastened within 10 seconds of an ignition on, the system generates an alarm signal for 5 seconds. So second point, we're going to take it as the alarm is turned off when the alarm time, that is 5 seconds, expires, or if the driver passenger fasten the belt, or if the ignition switch is turned off, whichever happens first. So next, here the states are alarm off, waiting, and alarm on, and the events are ignition on, ignition key off, time expire, alarm time expire, and the seat belt on. So using the FSM, the system requirements can be modeled using this figure. So the ignition key on event, so this one, the ignition key on event triggers the 10-second timer and the transition the state to waiting state. If a seat belt is on, the ignition key is off, event occurs during the wait state, the state transition into alarm off, it goes back, the arrow, what the arrow this showing. So when the waiting timer expires, the waiting state, the event timer expire. So this one, the event timer expire is generated and it transition the state to alarm on from the waiting state. So the alarm on state continues until a seat belt on or ignition key off event or alarm key expire event, whichever occurs first. The occurrence of any of these event transitions the state to alarm off state, alarm on state to alarm off state. The wait state is implemented using a timer. The timer also has certain set of states and events for the state transitions. So using the FSM finite state model, the timer can be modeled as ideal or ready or running. During the normal condition, when the timer is not running, in normal condition, when timer is not running, it is said to be in ideal state. The timer is said to be in ready state when the timer is loaded with the count corresponding to the required time delay, the timer remains in ready state until a start timer event occurs. So the timer changes its states to running from the ready state on receiving a start timer event and remains in running state until the timer count expires or stop timer event occurs. So the timer state changes to ideal from running on receiving a stop timer or timer expire event. So next, as an example, we're going to design an automatic tea coffee vending machine based on finite state model for the following event. So as an example, the tea or coffee vending machine is initiated by the user inserting a 5 rupee coin. After the inserting the coin, the user can either select a coffee or tea or press cancel to cancel the order and take back the coin. So here the FSM representation is done using this diagram. So there are 4 states: state A, state B, state C, and state D. So in this state A, what it will going to do, we will going to insert a coin. The action will be in OK state. So after inserting a coin, you need to press whether we need to display, or you need to press whether you need a tea or a coffee. So, or you can cancel. If you cancel the button, the action will be a coin out. It will go back to the state A and the coin will going to come out. So next, if you insert coin and it will going to ask whether for a coffee or a tea. So if it is of a tea, it will going to start C. If it is of a coffee, it will going to for state D. So here from state B, if you press for a T button, so it will going to dispense C. It will going to state C and it will going to dispense a T and the action done, and it will going to come back to its original state. So from here, if you press for a coffee, so it will going to dispense a coffee. After dispensing, it will going to back to an initial state. This is what the first example is of. So second example, as you guys know, which we are using as in telephone, public telephone unit based. So coin based public phone, where we have used in our childhoods. So in that, the process are the steps we are going to choose here are these. So the calling process is initiated by lifting the receiver of the telephone unit. So after lifting the phone, the user needs to insert a 1 rupee coin to make the call. If the line is busy, the coin is returned on placing the receiver back on the hook. If the line is through, the user is allowed to talk till 60 seconds, and at the end 45th second, the prompt for inserting another 1 rupee coin for continuing the call is initiated. If the user doesn't insert another 1 rupee coin, the call is terminated on completing the 60 seconds time slot. So here is the states. So here we're going to start from a state 1 and it will going to end it with a state F. So at the state 1, what it will going to do, the line, if the line is okay, it will going to action will be performed, this display is okay. If there is a fault in the line, it will going to display an error message. Okay, so now from start, it will going to start from state A. So event lift receiver, we will going to lift a receiver, it will going to show it as okay. So next event, what we will going to do, we will going to insert a coin. Okay, the action will be of okay. And it's state 3, what will in state C, what it will going to do, if it is of a valid number and invalid number, it will going to check whether it's a invalid number or it is a valid number. If it is of an invalid number, it display error and it will going to go for a state H and it will going to place a receiver back and the coin will going to return and it will going to an initial state. If the number is a valid one, we will going to dial and it will going to perform, it will going to go to a state D, and if it is of a line busy or it is in connecting mode, line will be connected. So again we have two, when is line is busy or line is available. if it is a line busy, it will going to display an error message and it will going to go for a state G, and you guys will going to place the receiver back and the coin will going to return. So if you connect the line has been connected, it will going to monitor the duration and it will going to go for state E. So after completion of 60 seconds, you need to place your receiver back and it will going to disconnect the line. So the timeout, that's what the timeout is. You are going to replace the receiver back. So if you insert a coin, it will going to continue your call, and event after calling, after talking, you need to place your receiver back. The action is done. Here we are not going to receive any of the coin. So this is what the example for a design of coin operated public telephone. Hope you guys have understood. So next is sequential program model. So sequential program model, in the functions or the processing requirements are executed in sequence as the name indicates. Here the program instructions are iterated and executed conditionally, and the data gets transferred to series of operations. So here the finite state machines are good choice for sequential program modeling. So here is the example. So here are the header files as defined on 1, off 0, S1, no 0. So here it's the flow diagram where the sequential key operates on flow chart. On the flow chart models the execution. So execution will be performed on the flow charts. So here there is a flow diagram. According to this, the program has been written. So void seat belt on, so ignition key on, wait for 10 seconds. So here the wait for 10 seconds. So next what it will going to do, it will going to check whether the ignition is on or off. So if ignition is on, that is S state. Why? If it is no, it will directly go to end. If it is of S, it will going to, if it is of, check for an ignition key on or off. So if it is on, seat belt ignition on, if it is of ignition on, it will going to check for a seat belt is fastened or not. So seat belt is fastened. If it is of S, it will going to get end. If the seat belt is not fastened, it will going to set for a timer. So set timer for 5 seconds and start alarm. Set timer for 5 seconds and start alarm. So after this, again it will going to check whether the ignition is on. If it is of S, again it will going to check for seat belt on. If it is of S, it will going to go for a stop alarm and it will going to get end. If it is no, again it will going to recheck this process. This is what the sequential is of. So next is concurrent communication process model. So as an example, here also we're going to take the seatbelt warning system in concurrent process model. So first we're going to see what do you mean by concurrent process model. So the concurrent communicating process models concurrently executing tasks or the processes. It is easier to implement certain requirements in concurrent processing model. So sequential execution leads to a single sequential execution of tasks and thereby leads to poor processor utilization when the task involves input-output waiting, sleeping or specified during, etc. So here we are going to split the tasks into 5. One is timer task, for which is for waiting for 10 seconds, task for checking the ignition key status, task for checking the seatbelt status, task for starting and stopping the alarm, alarm timer task for waiting for 5 seconds. So here we have 5 tasks and these are the tasks which they have been created. Create and initialize events. So that is wait timer expire, ignition on, ignition off, seatbelt on, seatbelt off, alarm timer start, alarm timer expire. Create task waiter time, create task ignition key status monitor, create task seatbelt status monitor, create task alarm control, task alarm timer. So here it is. So first wait timer task. So what it will going to does, it will going to sleep for 10 seconds and after that it will going to set an event wait timer expire. After the 10 seconds expire, it will going to check for alarm control task. So it will going to wait for the signaling of waiter timer expire. So after expiring, what it will going to do, it will going to check whether the ignition is on or the seat belt is off, and it will going to start an alarm. So set event alarm start. What it will going to do, it will going to perform this alarm timer task. Wait for the event alarm start, and it will going to wait, and it will going to check for 5 seconds, and set after setting this, it will going to return back alarm timer if it is of expired. So next, what it will going to do, ignition off or seat belt on. So this arrow marks will going to show what and all the things which will going to perform here. So the ignition seatbelt status monitor, what it will going to do, it will going to check whether the event belt is on or off. If it is off on, it will going to perform this operation. If it is off, it will going to perform this operation. And this is what the concurrent process program model is of. So next is object-oriented model. So the object-oriented model is an object-based model for modeling system requirement. It disseminates a complex software requirement into a simple, well-defined pieces called objects. So object-oriented model brings reusability, maintainability, productivity in system design. So in OOM, that is object-oriented modeling, object is an entity used for representing or modeling a particular piece of system. So each object is characterized by setting a unique behavior and state, and a class is an abstract description of a set of objects, and it can be considered as a blueprint of an object. So here these classes represent the state of an object, whether the member variables and the object behavior and the member functions. So here the private member variables and the functions are accessible only within the class, whereas the public variables and functions are accessible within the class as well as the outside the class. So the protected variables and functions are protected from external access. So the concept of object and class brings an abstraction, hiding, and protection. So this, thank you guys. This is what we have learned in today's class, and we're going to continue next class. Thank you guys.